Get it? Loose? No tension? I couldn't find a tension song. All right, so we're going to talk about songs that, not songs, we're going to talk about problems that involve tension. We're not really learning anything new in terms of equations or anything like that, but these problems will look very new and very intimidating at first, and then hopefully we'll be able to kind of dissect them down, and you guys will feel a lot better about them. So this is all talking about tension and equilibrium. So when an object is in equilibrium, what that means is that there is no net force on them. It doesn't mean that there are no forces in general. It means there are no net force on the object. So it means it's not accelerating. So either this object is at rest or it's moving at a constant velocity. The net force acting on it is 0, since the acceleration is 0. But like I said, it's kind of like tug of war. If I pull one side with 20 newtons and somebody else pulls another side with 20 newtons, maybe the object won't move, right? Nobody's going to be moving because they're both pulling with 20, but there are forces on them. It's just the net force is 0. So when an object is in equilibrium, it does not mean that there are no forces. It means that there is no net force. It's kind of sometimes easier to work in components, so you'll notice that sometimes I'll break up my net force in the x direction, and I'll break that from the net force in the y direction and just kind of work in each direction. But I'll go ahead and show you how that's done, but you can break it up into components. So drawing the free body diagrams is really important. So this is an equilibrium example. So we have this light here hanging from like some kind of ceiling or some kind of wall or something. And the light is not accelerating. It's hanging at rest. It doesn't mean there are no forces on it, right? So we have gravity pulling down. So what I do is I go ahead and the first free body diagram just shows the light. It shows gravity pulling down. It shows tension 3 pulling up. From that, tension 3 is actually being pulled up by tension 2 and tension 1. And so once you have this first free body diagram, it's really easy to figure out tension 3, but then breaking up tension 3 and tension 1 into tension 1 and tension 2 is kind of the trick. So there's 2 steps to the free body diagram. The first one, which is just on the object, and then the second one, which is from this point here, showing that tension 3 is also pulling down, and that tension 2 and tension 1 are what's keeping the light actually up. So we will do this example a little bit later, but this is how you draw the free body diagrams. So when you have multiple objects, the way that you want to solve it is you want to draw a free body diagram for each object. So that should be your first step, is to draw free body diagrams for each object and label which object is which for the free body diagrams. The second thing you want to do is apply Newton's laws to each object. So basically what you're going to end up doing is writing what I call a net force equation, or an F-net equation. And basically what that means is setting up all the forces on that object, adding them together, and then setting that equal to ma. Because remember, net force equals mass times acceleration. So we're going to add up all the forces, so that's how we're going to get the net force. And then we're going to set that equal to ma. And then we're going to solve. So multiple objects, this is one example. So we have a mass here, mass 1, and we have mass 2. And so what we would do is we would draw 2 free body diagrams, one for mass 1. So this one's for mass 1. So you have tension pulling up, and you have mass 1 times gravity pulling down. That's just the force of gravity, or the weight. Then the second one, you have mass 2, and you have the tension pulling up, and you have the force of gravity on mass 2 pulling down. In these types of problems, and we're going to see this example later also, but in these types of problems, you're going to want to set direction. So there's no plus or minus, right? There's no right or left. But there is clockwise and counterclockwise depending on which way this spins. And so you wouldn't want to just choose up as positive, because up would make both these tensions positive, but really they're fighting against each other, right? Because this one's pulling down here, this one's pulling down here. So I'll show you how we're going to tackle that a little bit later. But on these ones, you want to look for clockwise, counterclockwise direction. But you always want to draw 2 free body diagrams. When you're pulling multiple objects horizontally, this is really easy to do. What I do is I find out the total mass, so I just add up the mass of all 3 objects, and these would normally have mass labels on them. I figure out the total acceleration, and I figure out the total force for the entire system together. And then I analyze each of the tensions in these ropes separately. So basically, the hint that I use is that if I cut this rope, which of the boxes would fall off and not follow with the force? And so if I cut this rope, this third box would fall off. And so that means that this tension rope right here is really only responsible for this box. And so when you were trying to find the force here, you would just do the mass of this box times the acceleration of the entire system. Same thing, like if you were trying to find this tension and you cut this one, you can imagine cutting this, both of these blocks would fall off. And so this force would be equal to this mass plus this mass times the acceleration. And so it kind of works from there. We'll practice a lot of these. You're going to do the same thing with hanging objects. So if I cut this string, I lose both. And so that means that this string is responsible for the mass of this plus the mass of this times gravity. If I cut this one, I only lose the bottom one, and so this rope is only responsible for the mass of this guy times gravity. So we'll work through some of those. Connected objects, and we've seen a couple of these now. But this is a very typical problem, this table with one object on top, one object on the bottom. We will do an example like this. But the first thing that you want to do is draw a free body diagram for each object. So this one is for object 1. You have the normal force pushing up, that's the table, pushing up on the block. You have gravity pulling the object down, right, toward the table. In this case, since the box is not accelerating in that y direction, then we would say that the normal force and the weight of the box are equal, and it's in equilibrium in the y direction. In the x direction, we have the tension pulling to the right, and we would maybe have some kind of friction. We'll learn what this is later, but some kind of friction pulling to the left. And then on the second box, we would just have the mass. We have the tension pulling up and the weight pulling down. There are no x direction forces on this one. So what you would want to do is draw your free body diagrams, apply Newton's laws separately for each object, and then you would go ahead and solve for the acceleration or the tension. The acceleration is going to be the same for both boxes, just in different directions, and the tension is going to be the same because it's just all one string. So let's go ahead and start with our example. Okay, so this is the example. I kind of showed you the free body diagrams before, but we're going to go ahead and solve this example now. So this is a traffic light that weighs 1.00 times 10 to the 2, so basically 100 newtons. So I would go ahead and write that down. The weight equals 100 newtons. And go ahead and remember that weight is negative, and so I would write that weight equals negative 100 newtons. Hangs from a vertical cable tied to 2 other cables that are fastened to a support, as shown. The upper cables make angles of 37 and 53 with the horizontal. Find the tension in each of the 3 cables. So we're trying to find tension 1, tension 2, and tension 3. So I'm going to move you over to the dot cam, and we're going to go ahead and work this out. Okay, so here we are. So make sure this is focused. There we go. This is supposed to say 53. I realize it doesn't look like a 53 now that I see it. Okay, so what I've done is I've written down the weight. I've written down the 3 things I want. I've drawn the picture that they drew. And then I've drawn my first free body diagram of just the stoplight. So the dot represents the stoplight. If you look directly at the stoplight, the only 2 forces on it are tension 3 pulling up and and the force of gravity pulling down. And so I have my weight. Now I wrote mg because I wasn't sure if they were going to give me the mass or the weight. So now that I know that the weight is negative 100, I can go ahead and replace that. So this is equal to negative 100 newtons. And I'm looking for this. Now, the key is, right, is that our net force has to equal 0 because this thing is not moving. It's not accelerating. So that means that the net force, F net, for this picture, right, must be 0. And remember that net force equals mass times acceleration. So since it's not accelerating, this is 0. That means that this is correct. And then remember also that the net force is all the forces on the object added up. So we have tension 3, which is going in the directly positive direction, plus we have negative 100 pointing down in the negative direction. So we know that 0 equals T3 minus 100. So this should be really simple, that T3 equals 100 newtons. So we are done with T3. That should be the easiest part. Now, let's look at how we're going to figure out T1 and T2. So what we're going to do is draw another free body diagram, so I'll just draw it over here. So I'm drawing this little knot right here. I have T2 pulling out this way. I have T1 pulling out this way. And I really have the weight of that thing, right, or T3, which we know this is 100 newtons, pulling down this way. I would go ahead and make sure I draw my angles on here. So this is 53. And I know this is 37. And now we're going to try to work it out from there. So the big key to this problem is that you have 2 directions. You have x and y. So this thing is being pulled to the right and left, and it's also being pulled up and down. it's in equilibrium no matter which way you look at it, in x and in y. So we're going to work out some equations for the x direction, and we're going to work out some equations for the y direction. So in the x direction, we want to add up all of our forces. So we're basically going to find the net force in the x. And then we're going to find the net force in the y. And we know that both of them are going to be equal to 0 because it's not accelerating. So the net force in the x is all the forces in the x added up. So if we look at this diagram, we have 100 pulling down. That's not in the x direction. So we ignore that part. We have the component of this tension, right, the x component of this tension. So you can draw it there, or you could draw it here, but it needs to be facing to the right because that tension is pulling out to the right. So this is 53 also. So I know that in the x direction I have T2 cos 53 in the positive x direction, right? And then for T1, the x direction is actually pulling to the left, so that's going to be negative, so I'm going to have minus. And if you would do the same kind of geometry, right, we have T1 cos 37 for that one. I'm going to go ahead and move this net force in the y over a little bit just to keep our equations separate. So right now this is my equation, right, for the x direction. Now I can be done for a second. Let's go over to the y direction. Because right now I have two variables and only one equation. So I'm going to see if I can try to work that out. So in the y direction, I have my net force in the y direction. I know it equals 0. And I know that it involves all the up and down forces. So the down force, I have 100. So I have negative 100 pulling down. Plus, I have these two up pieces. I have the up from each one of the tensions. So I have the y direction of T2, and I have the y direction of T1. So over here it would be T2 sine 53. And over here I would have T1 sine 37. And they're both positive because they're both pulling up. So I have my down plus my ups, and they have to add up to 0. So now I have two equations, I have two unknowns, so I would maybe just solve this equation for one of the unknowns. So let's see, maybe, I don't know, T2. So let's move this over. So I have 0 equals T2 cos 53 minus T1 cos 37. Let's move this down a little bit. And so I would add that to the other side. So I have T2 cos 53 equals T1 cos 37. Just basically added that to the other side. Divide by cos 53, so T2 equals T1 cos 37 divided by cos 53. And then my natural inclination would be to get this number, just because I don't like to hang on to these cosine numbers here. So I would just do cos 37 divided by cos 53. Just be careful the way you put it in your calculator. So I get that T2 equals 1.33 T1. Now I can take that and plug it in for T2 here. So I go over to this equation and I have 0 equals negative 100 plus 1.33 T1 sine 53 plus T1 sine 37. And then I can go ahead and maybe combine 1.33 times sine 53. So, and I'm going to move this 100 over also. So I'm going to get 100 equals 1.06 T1 plus sine 37, which is 0.6 T1. So then I can add like terms. And I get that 100 equals 1.66 T1. Divide everything by 1.66 T1. Or sorry, divide everything by 1.66, and I get T1 equals 60.24. Since it's a tension, that means it's a force, so it's going to be in newtons. So I can go ahead back to the top of my page and I can fill in T1, which is 60.24 newtons. And then I'm going to come back to the bottom and I'm going to go ahead and find out what T2 is just based on this nice simple equation that I made before. So T1. So T2 would be 1.33 times 60.24. So T2 is 80.12 newtons. So then I can go back up here and put 80.12 newtons. And that's it. So that's what they wanted. So the really big trick, right, is the steps. And so I'll just write the steps of what I did over here. So when you're solving a problem like this, you draw free body diagrams first. Then you write FNet equations. So that's this one at first, right? That was my first one. My second one was my x direction FNet equation, this guy here. And my third one was my y direction FNet equation. And once you have those three equations, at least these two, this first one we could solve right away, but these two, once you have those, you're basically just doing math now, right? Because now you just have two variables, two unknowns. So the physics ends right about there. So you write your FNet equations and then use to solve for unknowns. Okay, so let's go ahead and move on to the next example. All right, so example 2. And I'm giving you a lot of examples because I really want you to see different problems so that you have some resources for examples, because these are tough problems and I want you to be able to make sure that you can solve these yourself, but so that you have examples. So a sled is tied to a tree on a frictionless snow-covered hill, as shown in the picture. If the sled weighs 77 newtons, so I'm going to put the weight of the sled is 77 newtons. I'll put negative, right, because weight's negative. Find the magnitude of the tension force T exerted by the rope on the sled, and that of the normal force N exerted by the hill on the sled. Okay, so we're trying to find the normal force, and we're trying to find the tension. Now, I don't know if I explained normal force to you guys last time, but basically normal force is any surface that pushes up on an object because the object is sitting on it. So right now my computer is sitting on a desk, and so there's a normal force from the desk on the computer, making sure that the computer just doesn't fall through the desk. I think I did talk about it in the last video. If you have questions on it, let me know in class. All right, so let's go ahead and do this problem. So I'm going to go ahead and draw a picture, because that's usually my first thing. So here's my tree, right, and my sled. I just draw a box, and there's a rope tied to the tree, and this is where the tension is. There's a normal force from the surface of the hill, so that's my normal force, and the normal force is always 90 degrees to the surface. It's always perpendicular. So it's the hill pushing up on the sled. So that's the normal force. Weight pushes down, so this is kind of acting like my free body diagram, but I will draw one on the side also. Weight is pulling straight down. It doesn't pull down the hill, it pulls straight down. Make sure that looks straight. So it pulls straight down. So this is my weight, and it's frictionless, so that's it. That's all of my forces. Now it says that this hill is, I believe, 30 degrees. Let's make sure. Yeah, 30 degrees. And so there's this weird trick, but basically if you draw your y-axis here, and you let this kind of be your x-axis, so that your x and your y are kind of tilty, this angle will match whatever the angle of the hill is, and so this will be 30 degrees. And the reason that's helpful will become obvious in just a second. So let's go ahead and draw ourselves a free body diagram. So if I draw my x and y this way, right, so here's my y, here's my x, right, I have my normal force pulling directly in the y, I have my tension pulling directly in the x, and I have my gravity, my weight, pulling 30 degrees right there. Right? So it may not be the exact same angle, but that's the picture. So what we want to do is try to figure out what's going on here. So this thing is in equilibrium, right? And so that means that it's not accelerating, so that all the net forces must be equal to the net force must be equal to 0. So I'm going to work in x and y again. So the way I'm going to choose is just random. I know my weight is negative 77. So what you want to do is you want to look at the weight as a vector that has these components. It has this component down the hill, and it also has this component toward the hill. So this is the weight in the y direction, this is the weight in the x direction. So while this sled is here, gravity is not only pulling it down the hill to make it go fast down here, but it's also doing a little bit of work in pulling it toward the hill so that it doesn't go flying off the hill. And so gravity has two pieces. It has the weight in the y and the weight in the x. That's really important. Now, the normal force is only in the y and the tension's only in the x, so that's going to make it kind of nice. So now that we have our free body diagram, let's write our equations. So the net force in the x, and this little sum signal means net force. We know it's going to be 0, right, because it's not accelerating. Now let's find all the forces in the x. So if we make up the hill positive, because it looks like it's to the right, then we'll say t is positive. And then we have wx going negative. Now we can find out what wx is because the negative 77 is really just the hypotenuse. So really we can change this to 0 equals t minus 77 sine 30. Because this is the opposite from the angle. Okay, so it's negative 77 sine 30. Now let's do the same thing for the y. Right? And actually, we could even just figure this out. Let's not even go to y yet. Let's just figure this one out. Let's just add 77 sine 30 to the other side. So I have 77 sine 30. So T, the tension, must be 38.5 newtons. That's it. That's what the tension has to be. Because that's what the force is pulling down, so the tension has to match that, because it's not accelerating. Now let's do the net force on the y. We know it's also going to be 0, right, because the sled is not accelerating off the hill this way or down toward the hill this way. So we know it's 0. We have the normal force in the positive y. And then we have the weight in the y direction in the down direction. So we go ahead and plug in what we know. We know that wy would be 77 cosine 30, right, because it's adjacent. And so now if we just do 77 cosine 30, we get 66.7 newtons for the normal force. And that's it. So that's everything. So in this case, this is kind of strange, but you'll see some problems like this with ramps or inclines, and you always want to break the weight up into components in this type of problem. It's just more convenient than if you drew it this way, and you had the weight going straight down. Then the normal force would be going at this weird angle, and the tension would be going at this weird angle. And then you'd have to worry about components of 2 vectors instead of just 1. So that's why I always suggest we don't do it this way, but that way would still work. This way is just a little bit easier in my opinion. So that's example 2. Now let's look at example 3 and then we'll be done. So example 3 says 2 objects, and I showed you this one kind of before. This is called an Atwood's machine. 2 objects of mass 1 and mass 2 with mass 2 greater than mass 1 are connected by a light inextensible cord, it just means it can't extend, and hung over a frictionless pulley. Both cord and pulley have a negligible mass. Find the magnitude of the acceleration of the system and the tension in the cord. So we want acceleration and we want the tension. I'm going to draw myself a picture. So I'll get you guys over here so you can see it. So this is example 3. So my picture looks like this. I have a pulley, and I have these 2 objects. And I'm not sure if I matched the same shape. No, I switched it. That's okay, doesn't matter. Mass 1, mass 2. Now they said mass 2 is bigger than mass 1. So you guys automatically should know that this thing will accelerate down this way in the clockwise direction. So will accelerate clockwise. Okay. Now I'm going to go ahead and set that clockwise is going to be positive. Anything working counterclockwise, that's what CCW means, is going to be negative. And I'm going to go ahead and I'm going to draw free body diagrams for each of these things. I'm not really sure how to start because I have no numbers. So we're just going to go ahead and try our best. We might have to just use variables. So for M1, I have the tension working upward, and it's going to be positive because it's pulling this box clockwise. Now down, I have mass 1 times gravity. And I know that's going to be negative because it's pulling it counterclockwise. The net force equation would be, right, so the net force is always equal to MA. That's our main equation for this. And so it's going to be, let's specify it for this one. So it's going to be mass 1 times mass 1's acceleration. Now mass 1's acceleration is going to be positive because it is going to go clockwise. So both accelerations are going to be positive because they're both going to move clockwise. that's equal to all the forces on mass 1 added up. So in this case right now we have T minus M1G. That's as much as we can do for now. Let's work on the second object. So here's object 2. We have a tension pulling up. It's the same tension, it's just in a different direction. So I'm going to make it negative because it's pulling counterclockwise. M2G, I'm going to make positive because it's pulling clockwise. The equation for this would be net force equals M2 times the acceleration, and that's going to be equal to all the forces on object 2. So it's going to be negative T plus M1G. So now they're asking us to find A and T, so I'm assuming they're going to actually just ask us in terms of variables. So once you've gotten here, you're done with the physics. Now it's all math. So we know the A's are going to be equal. We know what G is. It's 9.8. And we know that the T's are equal because it's just one string. And so they're going to be equal. So I just write one of these equations in terms of T maybe. So I'll just write this one as T equals M1A plus M1G. So I just move that to the other side. And then I'm going to write this equation same thing as in terms of T. So I'll add T to the other side and minus M2A. So I'll get T equals M1A minus M2A. I'm sorry, M1G. Oh shoot, this should be M2G. I'm sorry. This one should be M2. M2G minus M2A. There we go. All right, and then I can just go ahead and set these equations equal. So I have M1A plus M1G equals M2G minus M2A. Let's see. So if well, what are we trying to solve for? A. So let's just isolate A then. So I would probably add this one to the other side. So I'd have M1A plus M2A equals M2G minus M1G. And then let's pull A out of this. So this is just getting tricky math. I wouldn't really ask you to do this, but it's good practice, just in case the AP does. So all I did was just pull the A out like a reverse distributive property, and I'm just going to divide. So I have M2G minus M1G over M1 plus M2. And that's as far as we can get. Right? And then if we want the tension, we could really just plug this stuff in for this A here. So it'd be like M1 times M2G minus M1G over M1 plus M2 plus M1G. So really that's how we would maybe write the tension. So that's it. If you think you can simplify, that'd be better, but I don't know that there is any way to simplify this at this point. So that's it. The main point of this example, showing you this example, was about the clockwise, counterclockwise situation and kind of how to rate these, because it's going to be a little bit different than any other problem because of the counterclockwise instead of the up, down, left, right type of situation. So that's it. We will go ahead and practice a lot of these in class on Wednesday. So make sure you're writing down any questions that you're having, and you can go ahead and bring those up in class on Wednesday.